My 12.5-inch Dobsonian telescope that I designed and built has been great, as I'm sure you've heard many times on this channel. However, there are some aspects of the mechanical design that I haven't been quite satisfied with, so I made them better.
Say, build stuff!
The large altitude gears simply rest on the smaller roller gears, which in practice works, but it's not ideal as the gears are loaded radially. And gears are not intended to take load this way. They're really only intended to take load tangentially as the gear teeth push against each other. My new design incorporates a smooth surface on the outside edge of the gear. This supports all the radial load, basically all the mass of the telescope, so the gear teeth are just doing the pushing or the rotating as they're intended to do. I've also increased the modulus of the gear teeth from 1 to 1.25, so the gear teeth are a little bit larger, have a little bit more bite. Another improvement is how the large gears are broken up into smaller, printable-sized sections and then rejoined. Someone commented on one of my videos suggesting to split the gears along the tooth profile rather than just cutting straight through. This is so that when rejoined, there'll be minimal or zero seam. This was quite a bit trickier to model. However, I'm always up for a CAD challenge. Not a cat challenge, a CAD challenge. No, I'm up for a cat challenge too. Challenging. The next area to improve was the gear roller supports. In the original design, I was kind of trying to do too much with one part. The vertical bearing supports also function as part of the clamp for the carbon tubes for the main telescope base. This is less than ideal for a couple of reasons. Number one, the overall just lack of manufacturing accuracy with 3D printing. These walls are not necessarily going to be perfectly 90 degrees, especially when they're assembled and you put heat set inserts. And number two, and most importantly, was when you tighten the clamps on the bottom, the vertical walls can get pulled out of parallel by the clamp stretching and deforming. Having the walls be not parallel results in the two bearings supporting the gear shaft being not parallel and not concentric. Both of these issues result in binding in the bearings that support the roller gear shaft. The result is that the roller gear just doesn't quite roll as smooth and consistently as you would want. In practice, I was able to kind of just tweak and tune and adjust by how tight or loose I had the screws to get these to run smooth enough. However, that's not a very good mechanical solution. The new design adds an additional base part which mounts to the base clamps with a single screw. This allows the whole roller gear assembly to rotate, which can help with any misalignment between the front and rear roller gears. For the vertical bearing supports, I'm now using 3mm carbon fiber plate, which is super stiff and very flat. This results in the two bearings supporting the gear being parallel and concentric for a nice, smooth, consistent rotation of the gear. Also, more carbon fiber. This redesign also required a slightly tweaked altitude motor mount and a different drive gear. Okay, and after many days of printing, I've got all the parts, and I'm just going to lay them out and do a dry fitting. It's important to make sure everything fits together and looks good before you start adding adhesive. Also, off camera, I've done a bit of sanding on the mating surfaces just to make sure everything sits together nice and flat and square and looks good. 3D printed hexagonal pegs are used to help join the parts and align them. I'm using several different lengths of 15 millimeter carbon fiber tube for the structural elements. The assembly is a bit of a fiddly process, as everything kind of has to be aligned correctly, and then it kind of has to all sort of snap together all at one time. So it's important to do a little bit of a practice dry run, again, before adding adhesive. Now it's time for adhesive. I'm using my favorite structural epoxy, 3M's DP420. This epoxy is available in both a natural color and black, but the black is oftentimes hard to source, so I just add a drop of black dye. So any of the adhesive that shows through will, match a little bit better rather than having this sort of white goopy look. I'm applying a decent amount of epoxy to the surface. I don't want to do too much because I don't want it to, too much to squeeze out and ooze out and make a big mess. Particularly at the edges near the gear teeth. I don't want epoxy to squeeze out of the seam and then into the trough, the valley of the gear tooth profile because, well, then the gears won't work. It's also always kind of a race against the clock because this stuff has a decent working time of like around 20 minutes or so. But if you make some mistakes and have to fiddle a bit, then that working time can quickly get away from you. It's another reason why working with epoxies in general, whether it's structural adhesives or composites projects, that you really want to do like a dry run, a rehearsal, so you know all the steps ahead of time before you start mixing time-sensitive epoxy. You can see I've used masking tape to mask the adhesive line area edge of the tube so I don't get excessive epoxy smeared out on the tubes. This kind of works, it kind of doesn't work. The downside is that if epoxy does cover the tape, then you end up with a little bit of tape sort of trapped under cured epoxy. So I think the key here really is to remove the masking tape while the epoxy is not quite still wet, but still kind of tacky, so it's soft enough that it just sort of peels off. I've covered my work surface in parchment paper, like wax paper, which sort of works, but the epoxy won't cure to it, but it is sticky. You can see it kind of lifts up, and it kind of isn't the greatest solution, so this is something I could look to improve in the future. Then I'm just using spring clamps here to hold the seams of the 3D printed gears together. And the flat surfaces there actually, I think, do a pretty good job of aligning the parts so that they are, so everything's in the right shape while the epoxy cures. And then while the epoxy is still wet, use paper towels and rubbing alcohol to wipe up any excess that I can. 24 hours later, and it's time to remove the clamps and the tape. Then just a quick test to see how the mating roller gear rolls across the seam, and it seems like it's running pretty smooth. And then the process is repeated for the other side gear. Here's a close-up of one of the seams where two of the gear sections have been joined. There is a bit of a bump along the flat rolling surface, which I anticipated, and I can feel it as I roll the gear along the seam. The solution to that's pretty easy. I just get the file out, and I'll just file and smooth this transition over. And after that, the seam is buttery smooth. I don't know that I can really feel any type of a bump along here. So this is looking pretty good. Now we move on to the roller gear assemblies. One factor I didn't consider in the CAD design phase was how to attach the gears to the shafts. What I decided was to grind out some flat spots or some grooves on the shafts and then use adhesive to bond the gears in place on the shafts. My idea here is not to rely on the adhesive bonding to the stainless steel shafts, but instead have these deep grooves so that'll fill with epoxy, and then when the epoxy cures, it'll sort of mechanically lock it as much as forming a bond with the surface. The downside of this is that the gears are now permanently fixed to the shaft, so I have to measure and make sure the distance is correct, and then I can't adjust it later on. Okay, now we'll get back to the assembly of the actual roller gear mechanism. The bearings press into these 3D printed holders, which then will get epoxied onto the carbon fiber sheet vertical plates. I need to space the gear 2 millimeters from the vertical carbon fiber plates. To do that, I've got 2 sheets of 1 millimeter carbon fiber plate that are some leftover parts. So I really just need a 2 millimeter shim. This makes the whole process a little bit fiddly to assemble and then press the bearings onto the shaft, but it works. You might cringe at seeing these flathead screwdrivers pushing on the bearings, but I don't have a proper bearing press, and I'm making sure to press only on the interrace of the bearings, so I'm not pushing on the seals. If I was building a lot of these things, I would definitely invest the time into making or sourcing a proper bearing press tool. Checking to make sure that the shaft and bearing runs nice and smooth with no signs of binding or play or anything like that. Now it's time to bond the 3D printed bearing holders to the carbon fiber vertical plates. Bonding these parts after the assembly makes it a little bit awkward, but I'm doing this because with the shaft and bearings in place, I ensure that the bearing holders are going to have the bearings aligned and concentric. All the pre-assembly is done, and now it's time for the conversion. I decided to start with the altitude motor mount and drive gear. This uses a single ratcheting thumb screw for tightening and loosening, so I can quickly engage and disengage the motor when in use. I didn't have the right length M4 screws. Thankfully, Lowe's did have some in stock, but unfortunately they were Phillips head screws, which normally I wouldn't want to use, but I didn't want to wait, a day or two for Amazon. I wanted to get this project going. Okay, all 4 roller assemblies are installed, and now it's time for the first test roll with the large gear. And everything is running nice and smooth. This is feeling pretty good. So now I'll go ahead and install the Teflon dampers. Now we're on to assembling the altitude gear frame and getting it squared up. A tape measure is a rather poor and inaccurate way of doing this. Ideally, I'd have a template, a gauge that's set to the spacing that I want, so I can have a hard stop. But in lieu of that, we will make do with what we have. And just some little M3 set screws are enough to hold these tubes in position. Now we can test how the 2 large altitude gears assembled into a frame rolls on the base. It's a little bit fiddly at first and takes a bit of adjustment to get things running smooth. And here I've identified that one of the rollers is actually not quite sitting vertical. It's kind of pointed outwards a little bit, so it's not aligning with the other gears. It's a pretty simple adjustment of the base corner clamp to get this thing squared up. And now the assembly feels like it's rolling pretty consistent and smooth. So I'll move on and test fit the altitude drive motor and gear. Next step is attaching the mirror box to the altitude gear frame. This is another admittedly not ideal process and assembly. I have to use these little round clamps to hold the mirror box to the 15 millimeter carbon tubes of the frame. This is definitely an area where I could improve, but it does work, so we'll just stick with it for now. Also, I'm doing this with the mirror still inside the mirror box, so ideally I would probably remove that so I don't risk damaging the mirror if something falls or drops, but I guess I like to live dangerously. Okay, everything is assembled and working pretty good, and I got lucky with the forecast showed one clear night during the new moon, so I was able to get out to one of the closest dark sky sites. This is up in Panamint Valley, California, which is one valley to the west of Death Valley. The skies there are very dark. It's basically a Bortle 1 dark sky site, and it is pretty much in the middle of nowhere. Unfortunately, as you can see, there's quite a bit of high clouds as the sun is setting. That was not in the forecast. They did make a nice backdrop for a sunset time-lapse, though. My friend Dan and I sat around the campfire and drank beer, and perseverance would pay off because around 11:30 the skies did clear up, a bit hazy, but enough to do some astronomy. The new upgrades to the telescope worked quite well, and I also had my imaging rig out there doing some dark sky imaging for the first time. Thanks for checking out my video and the projects, guys. This was another fun one. I'm looking forward to bringing you a lot more. Check the links in the description for my Patreon if you'd like to support my work there. Also, my website and printables if you want to download and check out these files for yourself.